Hello everyone, this is Dr. A classes for BTech students. This lesson introduces the fundamental topic of mineralogy, a cornerstone of engineering geology. It delves into the study of minerals, their origin, physical and chemical properties, and their critical role in forming rocks and soils. It is designed to provide BTech civil engineering students with essential geological knowledge. Learning objectives of the course is understanding the definition and essential characteristics of minerals, classifying common rock-forming minerals based on their physical and chemical properties, describing how minerals form and change through geological processes, identifying key minerals using diagnostic physical properties, explaining the role of minerals in the formation of rocks and soils, assessing the importance of minerals in civil engineering and geotechnical applications. Minerals, the building block of Earth's materials. The solid crust of Earth is primarily made up of rocks, which are naturally occurring solid masses. These rocks are not uniform substances but are made up of aggregate of one or more minerals that are bound together in various proportions and structures. Each mineral within a rock retains its own physical and chemical identity, making minerals the most basic geological units that collectively build up the Earth's crust. What is a mineral? A mineral is defined as a naturally occurring, inorganic, solid substance with a definite chemical composition, having ordered internal crystal structure and formed through natural processes. Criteria for classifying a substance as a mineral. The criteria for a substance to qualify as a mineral are: it must have been formed through natural geological processes, it must have not been derived from organic material, it must be homogeneous, it must exist in solid form under Earth's surface conditions, it must have defined chemical composition, it must be crystalline in nature. Exceptions for definition of mineral. While minerals are defined by specific criteria, there are certain substances that are still classified as minerals despite lacking one or more standard characteristics. Synthetically produced gemstones such as diamond, rubies, sapphire, etc. are treated as minerals due to identical structure and properties. Organic substances such as coal, petroleum, and natural gas are organic in origin but classified as minerals in geology. Inhomogeneous minerals, example, amethyst, smoky quartz, bauxite, and kyanite, may have impurities or variable color yet are accepted as minerals. Non-solid forms, example petroleum, mercury, natural gas, and bitumen are semi-solid, liquid, or gas but still considered minerals. Isomorphic groups, example garnet, olivine, some pyroxene, and amphiboles, do not have a definite chemical composition yet considered a mineral. Cryptocrystalline minerals such as flint, chert, jasper, agate lack visible crystal structure but are classified as minerals. Ice as a mineral. Liquid water is not a mineral, but ice, when naturally formed, meets all mineral criteria. What is mineralogy? Mineralogy is the scientific study of minerals, their chemical composition, internal structure, physical properties, and classification. It is an essential area of study because minerals are the fundamental units that make up rocks and soils. Knowledge of mineral help civil engineers address key questions. What type of rock is present at the construction site? How will it perform under structural load? Is it susceptible to weathering or deterioration? For example, a granite rock contains minerals like quartz, feldspar, and mica. Each of these has different properties. Some are hard and durable, while others may alter under environmental conditions. This information is crucial during site investigation, foundation design, material selection, and even while assessing slope stability or erosion potential. Formation of minerals. Most of the minerals that make up the rocks around us form through the cooling of magma, which is a body of molten rock materials. Minerals crystallize as magma cools within or on the Earth's crust. The rapid cooling produces fine-grained or glassy texture with no visible crystals. A very rapid cooling forms volcanic glass having no crystals. Slow cooling produces large well-formed crystals. Other mineral formation processes. Minerals can also form in several other ways as follows. Precipitation from aqueous solution. Minerals can form by evaporation of lakes, seas or underground water. Metamorphism. New minerals form due to heat and pressure acting on existing rock. Biological processes formed by organisms. These are still considered minerals if they can also form inorganically. Classification of minerals. Minerals can be systematically classified based on their chemical composition, specifically the type of anion or anionic group they contain. This classification helps us understand their properties, behavior, and geological significance. The silicate minerals are by far the most abundant on Earth, making up to 90% of the crust. They are all built around the basic silicon oxygen tetrahedron and include common rock forming minerals like quartz, feldspar, and mica. Next are the carbonates like calcite and dolomite, which are key components of sedimentary rocks such as limestone and marble. Oxides and sulfides are economically important as many are ore minerals such as hematite and magnetite for iron, galena for lead, and pyrite for sulfur. Sulfates like gypsum often form from evaporating saline water, while halides such as halite rock salt are found in evaporite deposits. Phosphates such as apatite are vital for biological processes and are used in fertilizers. Finally, we have native elements like gold, silver, and graphite, which consist of single element and often occur in pure form. This classification not only helps us in identifying minerals but also plays a crucial role in understanding rock formation, resource extraction, and material behavior in engineering projects. Physical properties of minerals. Physical property of a mineral is an observable or measurable characteristics that help identify and distinguish that mineral from others without altering its chemical composition. These properties are determined by the mineral's internal structure and chemical makeup and include features like color, which is appearance in reflected light, streak, that is color of its powder form, luster, how it reflects light, example metallic, glassy, etc. Hardness, resistance to scratching measured on Mohs scale. Cleavage and fracture, how it breaks. Crystal form, external shape or habit. Specific gravity, that is relative density. Transparency, ability to transmit light, transparent, translucent, opaque. These properties are non-destructive and widely used in field and lab identification of minerals. Identifying minerals. To accurately identify a mineral in the field or laboratory, geologists rely on a set of distinct physical properties, many of which are easily observable or testable. Color is the most obvious property but often unreliable alone due to impurities. Instead, streak or the color of the mineral's powder provides a more consistent clue, useful especially for metallic minerals. Luster tells us how light interacts with a mineral's surface, whether it shines like metal, glass, or has a dull appearance. Transparency helps to distinguish minerals that allow light to pass like quartz or those that do not allow like galena. The crystal habit refers to the natural shape a mineral tends to form, while fracture tells us how it breaks when there are no planes of weakness. Some break smoothly, others irregularly. Now let us look at the testable properties which often involves a small physical process. The streak test involves rubbing a mineral across a ceramic plate to observe the color of its powder. Fracture is the way a mineral breaks when it does not split along cleavage planes. Quartz, for example, has a conchoidal fracture while others break irregularly. A key test is hardness, assessed using the Mohs hardness scale, where minerals are ranked from soft like talc to very hard like diamond. Finally, A specific gravity gives us a sense of how dense a mineral feels in hand. Galena, for instance, is much heavier than quartz of the same size. Together, these properties form a particular and effective toolkit for identifying minerals both in hand specimen and thin section. Crystal structure and their significance. Every mineral is defined not just by its chemical composition but also by the arrangement of its atom. This is what we call the crystal structure. At the most basic level, a crystal is formed when the atoms are stacked in repeating orderly pattern. This smallest repeating unit is called the unit cell, and it defines how the structure extends in three dimensions. There are several major crystal systems including cubic, hexagonal, tetragonal and more. These systems influence how a crystal grows and how it looks. For example, halite forms perfect cubes while quartz forms six-sided prism. But crystal structure is more than appearance. It directly affects physical properties. Take cleavage for example. Mica splits into thin sheets because of its layered crystal structure. Similarly, hardness is influenced by bond strength in the structure. Diamond and graphite are both made of carbon, but their structures give them entirely different hardness levels. In engineering geology, understanding crystal structure is vital. Rock with aligned crystal planes may split along those planes under stress. Sheet silicates can swell with water and cause instability in foundation. Even soil behavior can be influenced by the mineral present and their crystal form. So the crystal structure isn't just a mineralogical curiosity, it plays a critical role in both identifying minerals and in predicting how they'll behave in real-world geological engineering context. Common rock-forming minerals. When we study rocks, we are essentially studying aggregate of minerals. However, only a relatively small group of minerals called the common rock-forming minerals make up most of the Earth's crust. The most important group by far is the silicate. Built around the silicon-oxygen tetrahedron, these include feldspar, which are the most abundant minerals in the crust, quartz, well known for its resistance to weathering and its presence in many rock types, mica such as biotite and muscovite, which are sheet silicates, amphiboles and pyroxenes, which form dark minerals in igneous rocks, olivine, which is found in ultramafic rocks from the mantle. Next are the carbonates, particularly calcite and dolomite, which dominate sedimentary rocks like limestone and dolostone. We also have oxides such as hematite and magnetite, which are important economically as iron ores. Finally, sulfates like gypsum and halides like halite form the evaporite environments. These minerals are not only important for understanding rock types but also for interpreting Earth's processes and history, from igneous intrusion to sediment deposition and metamorphic transformation. Minerals and their engineering applications. Minerals are key components of rocks, soils, and construction materials, influencing the strength, durability, and sustainability of engineering projects. Engineering properties. Mineral properties such as hardness, specific gravity, reactivity, porosity, and cleavage affect the strength, durability, and performance of construction materials and soil behavior. Construction applications. Minerals like quartz, calcite, clay, gypsum, and hematite magnetite are used in making concrete, cement, bricks, plaster, and reinforced structures. Soil mechanics and foundation design. Mineralogy controls swelling, shrinkage, and load-bearing behavior of soils. Sustainability and resource use. Understanding materials enables efficient use of raw material, promotes recycling, and reduces environmental impact. Weathering and alteration of minerals. Weathering processes, whether physical, chemical, or biological, break down rocks and alter their mineral composition over time. This can weaken the rock mass, which is a major concern in construction and geotechnical design. Let us go through the key effects. Reduce load-bearing capacity. As weathered rocks turn into finer particles or clays, the strength of the soil or rock foundation decreases, posing risk for structural stability. Challenges in foundation design. Engineers must carefully assess the depth and extent of weathering to avoid placing foundation on unstable or highly altered layers. Increase erosion. Slopes and embankments composed of weathered materials are more prone to erosion, especially during heavy rains, leading to slope failure and maintenance issues. Degradation of construction materials. Weathered rock used as aggregate may have reduced strength, increased porosity, and poor bonding, making them less durable in concrete. Degradation of construction material. Weathered rock used as aggregate may have reduced strength, increased porosity, and poor bonding, making them less durable in concrete or road layers. Chemical instability. Altered minerals like clays can swell or shrink with moisture, react with cement, or degrade under environmental stress, affecting long-term durability. Need for testing. Because of these factors, it is essential to conduct thorough material testing and site investigation before construction. This helps engineers select appropriate material and adapt design to ensure safety and longevity. Advanced mineralogical analysis methods. Some of the advanced mineralogical analysis methods that are crucial for understanding the composition and properties of rocks and soils in civil engineering. X-ray diffraction. It is a powerful technique for identifying the crystal structure of minerals. By measuring the diffraction pattern of X-rays, we can not only identify the types of mineral present but also quantify their abundance. This is essential when assessing soil stability and rock strength for construction. Scanning electron microscopy. It provides detailed high resolution images of mineral surfaces, allowing us to observe the morphology and texture of mineral. This is especially useful when studying fine-grained materials and understanding their behavior under mechanical stress of weathering. Electron microbe analysis. It allows for precise localized chemical analysis of minerals at the micro scale. It helps us detect trace elements within minerals which can provide insight into their formation process and how they might behave in construction materials. Fourier transform infrared spectroscopy. It is used to measure the absorption of infrared light by minerals, which helps identify molecular vibrations. This method is particularly useful for studying clays and other fine-grained minerals as it provides a fingerprint of their chemical composition. Raman spectroscopy. Raman spectroscopy uses the interaction of light with the mineral's molecular structure to identify its chemical composition. It's a non-destructive technique that can be applied directly to field samples, making it ideal for on-site mineralogical analysis. X-ray fluorescence. It is a rapid and non-destructive technique for determining the elemental composition of minerals. It is particularly useful for bulk analysis, helping engineers determine the suitability of materials for construction based on their chemical makeup. These advanced techniques are essential for making informed decisions about material selection, construction, and environmental impact. In practice, these analyses help engineers and geologists better understand the behavior of minerals and rock under various conditions. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: what is a mineral? Discuss the fundamental characteristics that define a substance as a mineral. What is Mohs hardness scale and how is it used in mineral identification? What are the essential physical properties used in the identification of minerals and how do they aid in mineral classification? Explain the relationship between mineral composition and the engineering behavior of rocks. Explain how mineral identification can aid in site investigation and material selection in civil engineering. Discuss how the crystal structure of silicate minerals influences their physical properties and weathering behavior. Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thanks.